What if everything you think you know about the universe is built on a foundation that doesn't actually exist? Consider for a moment the stage upon which all physical events unfold. We call it spacetime. Einstein taught us that it curves, that it bends around massive objects, that it tells matter how to move, while matter tells spacetime how to curve. This elegant picture has dominated physics for over a century. We measure distances in space, intervals in time, and we treat these measurements as fundamental properties of reality itself. But what if space-time isn't fundamental at all? What if it's merely an emergent phenomenon, something that appears to exist only because of deeper processes we haven't fully grasped? The question isn't just philosophical speculation. It emerges from the sharpest edge of theoretical physics, where the mathematics of quantum mechanics collides violently with the geometry of general relativity. These two pillars of modern physics have given us extraordinary predictive power. Quantum mechanics describes the behavior of particles with stunning accuracy. General relativity describes gravity and the large-scale structure of the cosmos with equal precision. Yet they speak fundamentally incompatible languages, and at the boundary where they must meet, inside black holes or at the moment of the Big Bang, our equations break down completely. They produce infinities, nonsensical answers, predictions that cannot possibly be true. This breakdown suggests something profound. It suggests that we've been building our theories on the wrong foundation. We've been assuming that space-time is the arena in which physics happens, the canvas on which reality is painted. But perhaps space-time itself is the painting, not the canvas. Perhaps the true canvas lies deeper, in a realm where space and time don't exist as separate, measurable things, but where they emerge from something more fundamental. Let me take you through why physicists have started to think this way. The trouble begins when you try to apply quantum mechanics to gravity itself. In quantum field theory, we treat forces as arising from the exchange of particles. Electromagnetism comes from photons, the strong nuclear force from gluons. So we might imagine that gravity comes from gravitons, hypothetical particles that carry the gravitational force. But when we try to calculate what happens when gravitons interact with each other, the mathematics spirals into chaos. We get infinite answers to finite questions. We can't predict anything meaningful. This isn't just a technical inconvenience. It's a sign that something is conceptually wrong. The standard approach to quantum field theory assumes that spacetime exists as a smooth, continuous background on which quantum fields fluctuate. But gravity isn't just another field living in spacetime. Gravity is spacetime according to general relativity. Spacetime curves, and that curvature is gravity. So when we try to quantize gravity, we're trying to make the very fabric of space and time into something that fluctuates quantum mechanically. We're trying to make the stage itself uncertain, probabilistic, fuzzy at the smallest scales. This leads to a conceptual problem that cuts deeper than just mathematical difficulty. In quantum mechanics, we measure properties of systems against a background of space and time. We say a particle is here or there, that it moves from one point to another over some interval. But if space and time themselves are quantum mechanical, if they fluctuate and exist in superpositions of different geometries, then what does it even mean to say something happened at a particular place or time? The very framework we use to describe quantum events seems to presuppose that space-time is already there, fixed and definite. But if space-time itself is quantum, we've lost our footing entirely. This is where the idea of emergence becomes essential. Emergence is a concept we understand well in other contexts. Temperature, for example, doesn't exist for a single molecule. It only makes sense when you have vast numbers of particles moving randomly. Temperature emerges from the collective behavior of atoms and molecules, but it isn't a fundamental property of any individual particle. Similarly, the hardness of a diamond, the wetness of water, the flow of traffic on a highway, these are all emergent properties that arise from simpler, more fundamental interactions. Could space-time be like temperature? Could it be something that emerges when you have many quantum degrees of freedom interacting in particular ways, even though it has no meaning at the most fundamental level? This possibility has driven some of the most creative theoretical work in physics over the past few decades, and increasingly, evidence from multiple directions points toward the same radical conclusion. Space-time is not fundamental, it's emergent. Let me give you one line of reasoning that makes this concrete. It comes from studying black holes, those regions of space-time where gravity becomes so strong that not even light can escape. Black holes have a boundary called the event horizon. Once you cross it, you cannot come back. But here's something strange. Black holes have entropy. Entropy is a measure of disorder, of how many microscopic ways a system can be arranged while looking the same from the outside. The remarkable discovery made in the 1970s is that a black hole's entropy is proportional not to its volume, as you might expect, but to the area of its event horizon. This is deeply weird. If you think of a black hole as a three-dimensional object filled with stuff, you'd expect its entropy to scale with how much volume it has, just like the entropy of a box of gas scales with the volume of the box. But instead, the entropy scales with the surface area. It's as if all the information about what's inside the black hole is somehow encoded on its two-dimensional surface. This led to a bold proposal called the holographic principle. The idea is that the information content of any region of space might be fully encoded on the boundary of that region, on a surface one dimension lower. Just as a hologram on a two-dimensional film can encode a three-dimensional image, perhaps the physics inside a volume of space is completely determined by information on its boundary. If this is true, then the three-dimensional space we experience might itself be a kind of holographic projection, an emergent description of something fundamentally living on a lower dimensional boundary. This isn't science fiction. Physicists have found precise mathematical realizations of this idea, particularly in the context of string theory. In certain carefully constructed models, there is an exact correspondence between a theory of gravity in a higher dimensional spacetime and a quantum field theory without gravity living on the boundary of that spacetime. This is called the AdS-CFT correspondence, and it has been verified in countless calculations. In these examples, space-time with gravity emerges from quantum entanglement and correlations in a theory that doesn't have space-time to begin with. Entanglement is another crucial piece of this puzzle. When two quantum systems are entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein famously called this spooky action at a distance and was deeply uncomfortable with it. But entanglement is real, experimentally confirmed beyond any doubt. And recent work suggests that entanglement might be the fundamental glue that creates spacetime itself. Think about it this way: in quantum mechanics, particles don't have definite properties until you measure them. Before measurement, they exist in superpositions, multiple possible states at once. But particles can also be entangled such that their properties are correlated in ways that can't be explained by any local hidden variables. Now imagine a vast network of quantum degrees of freedom, all entangled with each other in intricate patterns. The structure of these entanglement patterns could define what we perceive as spatial relationships. Two regions of spacetime that are close together would correspond to quantum systems that are highly entangled. Regions that are far apart would correspond to systems with weak or no entanglement. In this view, distance itself emerges from entanglement structure. Spacetime geometry would be nothing more than a coarse-grained description of the pattern of quantum correlations in some underlying quantum system. When you change the entanglement, you change the geometry. If you could somehow remove all the entanglement between two regions, those regions would effectively become infinitely far apart, disconnected from each other. Spacetime would tear. The fabric of reality wouldn't be fabric at all, but a pattern of correlations that can be reshaped, created, destroyed. This leads to a radically different picture of what a black hole really is. In the emergent spacetime view, the event horizon isn't a physical surface. It's a boundary in the space of quantum information, a threshold beyond which entanglement patterns become so scrambled that we can no longer track what's happening from the outside. The growth of a black hole's entropy reflects an increase in the complexity of entanglement as matter falls in. And the famous information paradox, which asks what happens to information that falls into a black hole, becomes a question about how quantum information is encoded in entanglement patterns rather than about physical objects disappearing into an abyss. Now I want to be careful here about what is established and what is speculative. General relativity and quantum mechanics are established theories with overwhelming experimental support. The existence of black holes is established. The fact that black holes have entropy is established through theoretical reasoning that connects thermodynamics to gravity, though we haven't directly measured a black hole's temperature or watched it evaporate. The holographic principle is a well-motivated theoretical conjecture with strong mathematical support in specific contexts, but it's not experimentally verified. The idea that spacetime emerges from entanglement is even more speculative, though it's taken seriously by many researchers because it offers potential solutions to deep conceptual problems. What's not speculative is the problem itself. We know that general relativity and quantum mechanics are incompatible in their current forms. We know that at the smallest scales, around the Planck length, which is about 10 to the minus 35 meters, quantum effects of gravity must become important. We know that our current theories break down there, so something has to give. Either quantum mechanics is wrong in some subtle way we haven't detected, or general relativity is wrong, or more likely both are approximations to a deeper theory. The proposition that space-time is emergent rather than fundamental offers a potential way out. If space-time doesn't exist at the Planck scale, then there's no contradiction in trying to quantize something that isn't there. Instead, we need a quantum theory of whatever the fundamental degrees of freedom are, and space-time would emerge from that theory as a useful description at larger scales, just as fluid dynamics emerges from molecular physics, even though concepts like viscosity and pressure have no meaning for individual molecules. Several research programs are pursuing this idea from different angles. Loop quantum gravity attempts to quantize spacetime directly by treating it as woven from discrete loops and networks. In this picture, spacetime has an atomic structure at the Planck scale, and what we call geometry emerges from the quantum states of these networks. String theory, on the other hand, replaces point particles with one-dimensional strings and requires extra dimensions of space to be mathematically consistent. In string theory, spacetime geometry arises from the ways strings can vibrate and interact. Causal set theory proposes that spacetime is fundamentally discrete, made of a vast number of point-like events connected by causal relationships, with the smooth spacetime of our experience emerging statistically from this discrete structure. Each of these approaches has strengths and weaknesses. None has yet made predictions that we can test experimentally. This is the challenge of quantum gravity research. The energy scales where quantum gravitational effects become strong are so extreme, about 10 to the 19 billion electron volts, that we cannot reach them with any conceivable particle accelerator. We're forced to rely on mathematical consistency, theoretical elegance, and indirect hints from cosmology and astrophysics. But the implications of emergent spacetime extend far beyond just solving technical problems in physics. If spacetime is emergent, then time itself is emergent. The flow of time, the distinction between past and future, the arrow of time that points from lower to higher entropy, all of these would be features of the emergent description, not properties of fundamental reality. At the deepest level, there might be no time at all, just a timeless quantum state from which the appearance of temporal evolution emerges. This is profoundly disorienting. Our entire experience is structured by time. We remember the past, we experience the present, we anticipate the future. Cause precedes effect. We age, we change. Events unfold in sequence. How can time not be real? Yet physics has been hinting at the insubstantiality of time for a long time. In special relativity, the distinction between past, present, and future depends on your state of motion. Events that are simultaneous for one observer occur at different times for another. In general relativity, time can slow down, speed up, even stop at an event horizon. Time is already something relative and malleable, not the absolute backdrop Newton imagined. If we take the final step and accept that time emerges from something timeless, we are forced to rethink causality itself. In the emergent picture, what we call cause and effect would be correlations in the underlying quantum state that we interpret as temporal succession when we coarse-grain to macroscopic scales. The fundamental theory would be a quantum description without time, and the dynamical laws we observe, the differential equations that govern how fields evolve, would emerge as approximations valid in certain regimes. Some researchers have explored what physics without time might look like. In canonical quantum gravity, there's something called the Wheeler-DeWitt equation, which describes the quantum state of the entire universe. This equation has no time variable in it. It's a constraint equation that the quantum state must satisfy, not an evolution equation that tells you how the state changes with time. From within this timeless quantum state, observers like us perceive a flow of time because of the particular correlations between different parts of the system, between our memories and the state of the environment, between clocks and events. This is where physics touches philosophy in the deepest way. If space-time is emergent, if time is emergent, what does that mean for our understanding of existence, of being, of reality? Are we, as conscious observers embedded in space-time, also emergent phenomena? Is consciousness itself something that arises from the pattern of quantum correlations, or does it somehow touch a deeper level of reality that we don't yet understand? I don't have answers to these questions. I don't think anyone does. But I think the questions themselves are transformed by the idea of emergent space-time. We can no longer simply assume that the world of our experience, the world of objects located in space and events happening in time, is a faithful representation of fundamental reality. Instead, we might be like inhabitants of Plato's cave, perceiving shadows on the wall and mistaking them for the true forms that cast them. Yet this doesn't make space-time an illusion in the usual sense. An illusion is something false, something that misleads us. But emergent phenomena are real at their own level of description. Temperature is real, even though it's not a fundamental property of atoms. Water is really wet, even though wetness isn't a property of individual H2O molecules. Similarly, space-time is real as an emergent structure. The fact that we can measure distances, that clocks tick, that gravity bends light, all of this is real and describable with extraordinary precision by general relativity. The point is that this emergent reality is not the deepest level. There's something beneath it, something from which it arises. Understanding emergent space-time might ultimately require a shift in how we think about what it means for something to be fundamental. We're used to thinking of fundamental physics as describing the smallest building blocks, the elementary particles and forces from which everything else is constructed. But perhaps fundamentality isn't about size or scale. Perhaps it's about logical priority, about which concepts can be defined without presupposing others. In this sense, quantum information, entanglement, probability amplitudes, these might be more fundamental than space, time, and matter, even though we usually think of them as abstract mathematical tools for describing physical systems. If this is right, then the universe at its core is not made of things located in space-time, but of information, of correlations, of possibilities that actualize themselves in patterns we interpret as physical reality. This is a strange and beautiful picture. It suggests that the boundary between the physical and the mathematical might be less clear than we thought. It suggests that the unreasonable effectiveness of mathematics in physics, which has puzzled philosophers for centuries, might have a deeper explanation. If physical reality emerges from mathematical structure, from patterns of information obeying quantum rules, then perhaps mathematics is effective because the universe is mathematical at its foundation. Of course, all of this remains speculative in important ways. We don't yet have a complete theory of quantum gravity. We don't know exactly what the fundamental degrees of freedom are from which space-time emerges. We don't know how to recover all the features of general relativity from a microscopic quantum theory in full generality. These are hard problems, perhaps the hardest problems in physics, and they may take decades or longer to fully resolve. But the direction of progress is clear. Multiple independent lines of theoretical reasoning point toward the same conclusion. Space-time is not fundamental. The arena in which physics unfolds is itself a product of physics, an emergent structure that appears when we look at something deeper in the right way. This represents a conceptual revolution as profound as the shift from Newtonian absolute space and time to Einstein's relativistic space-time. It changes what we think the universe is made of at the deepest level, and it leaves us with a question that bridges physics and philosophy. If the stage itself emerges from the play, if the container emerges from the contents, if space and time are not the bedrock but the architecture, then what is the bedrock? What are we ultimately when the coordinates of space-time no longer apply? What remains when position and duration dissolve into the quantum correlations from which they arose? Perhaps we are patterns of information that have become complex enough to reflect upon themselves, to wonder about their own nature, to probe the foundations of their own existence. Perhaps the deepest reality is not a thing, but a process, Not a substance, but a relation, not a fact, but a possibility space that actualizes itself in the structures we call matter and space and time. We are still at the beginning of understanding this. The mathematics is fierce, the concepts are abstract, and the experimental evidence is indirect. But the implications are staggering. If spacetime is emergent, then the story of physics over the past century has been a story of peeling back layers, discovering that what we thought was fundamental was actually derivative. First, we learned that space and time are unified into spacetime, then that spacetime is curved and dynamical. Now we're learning that spacetime itself might not be the final layer, something deeper awaits. And perhaps the most remarkable thing is that we can even ask these questions, that we can use mathematics and logic and creativity to probe beyond the veil of immediate experience and glimpse structures that underlie reality itself. That capacity might be the most mysterious thing of all. Think about that. And if this exploration has sparked something in you, if you want to continue questioning what we think we know about reality, then join us here at What is Real as we keep pushing against the boundaries of understanding.